Okay, thank you. All right, so I'm Artem. I'm going to present this work, Correctness performance. I'm from the University of Southampton, and this is a joint work with Troels Henriksen, who's from the University of Copenhagen. Let me start with a little bit of motivation. So we are looking into numerical applications, and we observe two kinds of numerical applications that are out there. First kind is the ones that are written in low-level languages like C or Fortran, or maybe in Python with wrappers around high-performance libraries. They typically run very fast, but they have very poor correctness guarantees, specifically if we talk about formal correctness. It's very difficult to formally tell that they do things that they're supposed to. The other kind is ones that are written in, say, theorem proofs like Lean, Rock, or Agda. They specify very nice data structures, and they can have even high complexity, like ABL trees, but they rarely designed to run efficiently. So the question that we're asking ourselves is how to combine these two kinds in a single one, right? So can we envision a way to write numerical applications, have some nice correctness guarantees of our choice, and that still run efficiently? When people hear this question, the immediate reaction is typically, oh, well, sure, but we need a single language. And the vision that we're trying to put forward in this research is that, well, maybe single language is all good if it exists, but maybe in the meantime, it is better to follow the following compromise. You want to combine a dependently typed proof assistant, just a proof assistant, to do correctness engineering in, and high performance language to actually generate efficient code. And maybe for now, it could be a good compromise if these things would work in collaboration. Okay? In particular, we want to look into combination and Futhark. So Agda is the dependently typed theorem proof. We want to write specifications. It is about our specifications in Agda, then generate some code to Futhark, which is an almost trained language that is famous for generating very efficient code, runs on GPUs, right? So we take care of all kinds of low-level details that you typically think about, like parallelism, word groups, all kinds of stuff. In order to test whether this idea is realistic or not, we're implementing a canonical convolutional neural network. We implement automatic differentiation for it to perform some training. We extract the code and program, give it to Futhark, and try to run it and see how it works. Okay. In order to get there, so in this actual the paper, so first we define a theory, and if we follow lessons that we learned from EPL, that if we want to define numerical applications, it's to do this by defining a bunch of rank polymorphic combinators. Rank polymorphic means we extract over the number of dimensions in the arrays, and then if you put them, if you define the composition of these combinators, you end up with a very general, nice looking a numerical application. So we do this for the CNN. This doesn't give us a way to analyze the expressions, analyze the problems. In order to do this, we're going to define a DSL. It's going to be a deeply embedded DSL. And in this DSL, well, first of all, we're going to define conveniences like high-order abstract style wrappers. You can write nice programs in it, do not find the redundancies. Then we're going to define automatic differentiation as a function from E3. So, which means that we could immediately high-order differentiation if we want to. Then we define and prove that it is semantically preserving. And we need the optimizer to get rid of certain artifacts that are introduced by automatic differentiation that don't necessarily perform very nicely. Then we extract the Futhark, and then we see how I won't be able to cover all these details, all these things in the talk. I'm only going to make a high-level overview. So invite you to read the paper for actually understanding details in case you're interested. So, a high-level overview. Let's start with specifying what exactly is this example. So we're looking into a convolutional neural network for digit recognition. That's trained on SSM data. It is basically a lot of convolutional neural. This is very well understood in example that has been made. And among other things, it has been implemented in array languages. For this is the code that you see in the array languages. It doesn't matter what it says, but the point here is all of these functions are implemented as array expressions. So SAC is not specifically designed to write networks. It's just a general purpose array language. The formulation of the neural network is very compact, and it runs quite efficiently. So the problem with this is that SAC as a high performance language doesn't give correctness guarantees. So it gives you like C-like properties, but not really. And it didn't do automatic differentiation. So everything there was implemented manually. So we want to take the inspiration from this and bring it to the kind of theory. So in order to do this, we have to define array theory. We have to define, and the key idea of the representation of arrays calls a very kind of old functional mantra that could present your data as functions and as functions compose, right? And we do exactly this. Our arrays as functions values, and we take care of. You should be able to define combinators, because if you don't, then something loop nest around your code is not generic enough. Okay, so let's look at code. So this is our array. Let's go to kind of bottom up. So this is an array type. It's an array of shape S and element type X. Is a function from positions that are valid for the shape X into values of X. So what is the shape S? Shape S is a list of natural numbers. Your nil, this is your cons. And what are the valid indices for the given shape? It's a list of natural numbers where every element is where every element is less than in the shape, right? So it's a dependent type, so it's indexed by the shape, and fin n is a natural number that is bound by n, including n. Okay, so this definition by design is index safe. If you want to index your array, you have to guarantee that the index respects boundaries, and we have defined shape as a single object, so we can abstract over shapes easily and quite nicely. How does it? Okay, if you know containers, the Gauss form of a container, yes, yeah, right. But if you don't, then this is just what it means. So arrays are very rich, and they have all kinds of nice properties. For example, if we fix the shape S, then our S is an applicative functor. You can enjoy all the done with it. For example, define a constant array where all the values, like a K combinator, map, which is just a map. We can define zip width, which is of a binary function for two argument arrays. And so arrays are traversable. So plenty of things that make for just this function representation. Then we have array-specific combinators that come from the shape and non-trivial. So if we define shape concatenation, then we can switch between an array of concatenated shape and a nested array of respective shapes. And we can go back and forth, and this looks a bit like monadic join, or you can think about some form of currying, but these differentiations, these views of array are basically morphic because our arrays are okay. Then let's look at more specific combinators, and let's look how in this framework a convolution is going to be defined. So in order to define a convolution, it is useful to define a notion of slide. Well, first of all, let's make shortcuts of vectors, which are one-dimensional arrays. So the vector of length m is an array of iota is a singleton list. Indices into positions into shapes. Then we define this operation slide, which says if you have a vector, if you have a vector of length m and you have an offset, I can select a vector of length 1 plus n starting from the offset m. And basically the simply just, you add indices as you go, and that's your basic subvector. Okay. And then in order to define the convolution, all you do, you take the way that you convolve weights, and then you split array A as many times as you have inside of the array W. W, you slide array set, you multiply these corresponding weights, and then you together pointwise, right? This is your one-dimensional convolution. Okay, the details are not that good, but you can see that this definition is really straightforward. And the other nice thing that it's immediately generalized to rank n. So you can find it for n-dimensional arrays and pretty much the same stuff. You need to be able to slide dimensions. For this, you need to go from the summation of shapes. So you have to define sum of shapes pointwise. You have to define a successor of a shape, basically as one element in this, and then you can define an n-dimensional convolution. In pretty much the same way as one-dimensional. You have to update your slides to n dimensions. You have to update your n dimensions. Right. If we define a bunch of more combinators, write down a specific convolutional neural network like this, right? Again, the details are not very details are not more sophisticated than what we've shown before, but you can see that this definition is by construction index safe. These combinators have some properties that I talk about, and we didn't have to write any proofs, right? And it looks very much like that I started in signal science. Okay, so far so good, but this is especially in Agda, so we can run the performance that we have. So we still need to do some stuff to get all of the structural, and that's where we introduce. And we're going to introduce the DSL intrinsic style. So we want to eliminate the possibility to write expressions inside of the DSL. So what are the expressions we're to deal with at all? And it turns out for specifically these numerical examples, it is good enough to assume that we're dealing with these or some imaginary real number. We have to talk about the point is that it's the same for all arrays, so we can avoid this entirely. So the values that we want in our language are either arrays of shape S or indices of shape S. This is it. We don't want anything else. Then we use a standard. There's a SNOC list of these ASs. We define the proof relevant dependent variables. And this is how our DSL looks like. So again, don't read the code too much. It is a small language, so we just have variables, constants, array constructors, summation, some predicate on indices, slide back slides, as you see, in order to implement convolution, some arithmetic, and most importantly, local net binding. This thing allows us to talk about sharing some computations between these expressions, well, between the expressions, because it is. Okay, so I'm going to skip the evaluation so we can evaluate the syntactic back into Agda expressions. So we can introduce these wrappers to explain this, and if we do all this, then something find a syntactic version neural network. It's an expression in E, and we have to define these combinators in E. But if we do this, we get basically this piece of syntax and interpret this and see that it basically the Agda expression stuff. Okay, what do we do with the piece of syntax? Well, we want to do automatic differentiation. We do a reverse mode automatic differentiation. And the complication here is that we do this in this intrinsic settings. We have to take care of making sure that the shapes and all the variables are preserved. And the structure that makes it all work is this vector of arrays of a certain shape, right? So we want to compute derivatives for all the three variables in our code. So we take a context and we define environment index with two contexts. So environment gamma delta means that we have gamma many expressions in the context delta. And the types of these expressions, they correspond to the positions inside of gamma. Right, it's typical trick in this intrinsic encoding. Then we do not care about indices, so we can throw away all indices because they do not contribute to. They never contribute to the computations. So we don't have to compute derivatives. And then the trick that we haven't seen, which is very useful, we do additionally to this. We say that the action structure we work with is this extended environment, which is which is defined either as a normal environment or a lead binding that all the expressions in the environment can see, right? So we can introduce lead binding for the entire environment. This is the way that differentiation can preserve the right amount of sharing. Okay. So here's the how it looks like. Again, don't read the code too much. Basically, just get a general impression. So it's a function from an expression in E, a seed, and it's basically it computes updates of the environment, and you start with the environment that is full of zeros. So what is interesting about this code is it is defined in terms of updates on the entire array. So we never of actual elements as you typically do in gradients and mathematics. So this is kind of short. It is by construction terminating as because all the Agda terminating it. It is well scoped and it's well typed. It doesn't guarantee that this particular implementation computes the derivatives as you know them from calculus. If you think about epsilons and deltas. But hopefully, again, it's good enough to take this as a specification because we can look at this and see whether it makes sense. It pretty much it follows the standard rules of differentiation that you can read in the book. Okay, I'm going to skip the optimizer. We can optimize and we can prove that each optimization preserves the semantics. It's standard. We do code generation. And let me talk a little bit about performance. So we co-generate, we give it to Futhark this on the GPU, and so is that if compared with the TensorFlow, which is industrial strength machine learning framework, then for small sizes we're a bit faster, for large sizes we're a bit slower. But the important bit is, look, we are in the same ballpark as the industrial strength framework. And we picked a very tough example to compete with because, it has death, right? It's a hello world of TensorFlow. It basically it is being mapped to specific hardware units of a GPU that we do. But the point is, look, this is, in my books, is good enough, right? Which means to me that the approach where you combine theory and performance language is a reasonable thing to do, right? So they could coexist, and here's demonstrate that this is awesome. I think I should stop and be able to accept your questions after the announcement. For PhD students in Southampton who would be interested in doing something in time theory and high performance computing, a section of both. If you want to talk about it, if you're interested, please. And now I'm happy to take your questions.
Okay, thank you. Since we got a bit of a late start, I think we probably have time for like one question. If someone has a, could you please use the mic?
Sorry, I almost don't hear you.
So my question is about rank polymorphism. So is it possible to let after shape inference with, let's call them shape variables, and then we need to assume it's the smallest shape to satisfy the shape inference problem?
Sorry, can the chair repeat the question? I have trouble hearing what.
For rank polymorphism, you have a shape inference problem.
I heard shape inference, but I don't quite understand.
So after shape inference, can you have shape variables left over? And you need to assume that.
Can I have shape variables left? Sorry, can the chair repeat the question? I can hear the chair very well, but I can't hear the.
Hello, do you hear me better? Or maybe it's.
Oh yes, I can hear now. Yes.
Sorry.
Yeah.
So do you have a shape inference problem for the rank polymorphism that you offer, that where you solve shape constraints?
Right. Yeah, sure. Everything here is manually, so we don't have any magic. So I mean, you would have to. We don't. Well, we do as much inference as Agda does. It has some local inference, but of course, if you have some crazy expressions in the shape that are symbolic, you have to make sure that they match. And in principle, you can find yourself in a situation that you will have to write proofs. But for the cases where the shapes are static, then typically it's enough of the information for the local inference to kick in and resolve this.
Do you have leftover shape variables where you need to guess the smallest shape at the end? Or you need to assume the smallest shape? Where
I'm
it
not
could be
sure what do you mean? Leftover variables. I mean, we're just doing unification. So I mean, the shapes are we don't have any subtyping or subshaping. So we have to unify on the shapes, and if you have different expressions that mean the same thing, then you have to introduce casting. So you have to
Thank you.
define a proof that they're the same. There's no automation in this bit.
Okay, thank you. Let's thank the speaker again.